Hello. Okay. Here today in this video, we'll talk about similarity and diagonalization. That is another section in chapter 4. We were talking about eigenvalues and eigenvectors. So actually, we'll have maybe 2 or 3 short videos about similarity and diagonalization. Okay. As you saw in the last section, triangular and diagonal matrices are nice in the sense that their eigenvalues are transparently displayed, because we know that if you remember when we talk about a diagonal matrix, right? For example, let's say something like this. Say here we have 1, 2, 3. Here we have 0, 3. Let's say 5 and 0, 0. Let's say 6. So if we have something like this, right? And here we can just find what is it? Let's say matrix A. And what are the eigenvalues of this matrix? From here, we know that eigenvalues are the entries in the main diagonal, right? And also, if you're given another matrix here, let's say here we have 3, 0, 0, 0, -7, let's say 0, 0, 0, 6. This is also another diagonal matrix, not B. Let me just use D for this. Okay. From here, transparently, we can see that actually the entries in the main diagonal, they just give us, what is it, the eigenvalues of this matrix. So that's why we are saying that it would be pleasant if we could relate a given square matrix to a triangular or diagonal one in such a way that they had exactly the same eigenvalues. We know that if we're given a certain matrix by applying a bunch of elementary raw operations, we can actually bring this into this form, in the form of this A, right? And also even we can bring this into this form, D, that is, what is it? Uh, Reduced to echelon form, even we can have some ones here, whatever it is, right? But unfortunately, when you just apply elementary raw operations to reduce a given matrix into diagonal form, these operations do not preserve, what is it, eigenvalues here. Also, actually, it changes the eigenvalue of the matrix, which is not good for us. So actually, one method, what we did here is, what is it, converting a square matrix into triangular form using Gaussian elimination. So now in this section, we're going to study a different sort of transformation of a matrix that does behave well with respect to eigenvalues. Okay, now let's start with this definition, similar matrices. So let A and B be n by n matrices, square matrices. We say that A is similar to B if there is an invertible, because we are not saying that A is always similar to B. If there is an invertible n by n matrix P such that P inverse A, P inverse times A times P, that's equal to B. So can we just find such matrix P when you just multiply its inverse by A and by P, so it gives us this B. If it is so, then we say that A is similar to B, and we write it as A is similar to B. Now, from this definition, we can say that also B is similar to A. If we want to say that actually B is similar to A, then we should be able to find some invertible matrix Q, where Q inverse times Q inverse times B times here we have Q. If that thing is equal to A, then we say that B is similar to A. Actually, so we are going to prove this actually. If A is similar to B, then also B is similar to A. So from this definition, we cannot actually, without this, we cannot draw this conclusion. Anyway, let's see this example. That matrix A is this 1, 2, 0, minus 1, and B 1, 0, minus 2, minus 1. Okay. So here, these two matrices are similar. Why? Because if you just multiply this by, because from the definition here, again, since P is invertible, P inverse A, and here we have P is equal to B, means if you just multiply both sides by P on the left, what do we have here? Here we have P, P inverse A, P is equal to P, B. P inverse times P times P inverse, that's equal to I. So here we have AP equals P B. Actually, these two equations are equivalent. They actually express the same thing. So as I say here, to actually determine that if given two matrices are similar or not, we don't have to evaluate its what is it? Its inverse. If actually just substitute here, if A times P equals P times B, where P is invertible matrix, then we say that A is similar to B. So from here, what is our P? Our P is, I just choose this P as this matrix. This one is P. And this one is P. They are equal. If you just multiply the left-hand side, for example, what we have here, 1 times 1, 1 plus 2 times 1, 2, that's equal to 3. 1 time, negative 1 times 1, negative 1, 1 times 2, it is 2. Their sum is 1. And the second row by the first column, 0. Here we have minus 1. Minus 1 is 0. Here we have minus 1. And how about on the right-hand side? Here we have 1. Negative 1 times negative 3 is 2. Their sum is 3. 0 times 1, 0. Negative 1 times negative 1, that's equal to 1. 1 times 1, 1. 1 times negative 2, negative 2. Their sum is negative 1. And 1 times 0 is 0, plus 1 times negative 1, that's equal to negative 1. Let's see here on the left and on the right, we have exactly the same two matrices, so that they are equal. So our P matrix is this, 1 minus 1, P 1 and 1. So from here, we can say that these two matrices are, actually A is similar to B. That is how we define the similarity between matrices. Okay, so immediately now we have small theorem here. If let A, B, and C be n by n matrices, then it says that every matrix is similar to itself. Every square matrix is similar to itself, right? Actual proof is easy. Why? Because as P, for example, matrix P, I can take identity matrix. There's no any condition about choosing P, right? Because P is any matrix that must be just invertible. So we know that identity matrix is invertible, and it is inverse is equal to itself. So if you just substitute here, we know that I inverse times A times I, which is equal to I inverse equals I. Here we have A times I is A, that's equal to A. So that means that since our P is this I, then A is similar to itself. That is a proof of the first part. And how about the second part? It says that if A is similar to B, then also B is similar to A. So by definition, what does A is similar to B mean? We know that actually this is given. A is similar to B. That means that we can find some invertible matrix P where P inverse times A times P, that's equal to B. So now I'm going to show that actually also I can find some matrix where Q inverse times B times Q is equal to A. To do this one, if you multiply both sides by P on the left by P inverse on the right, what we have here. So A will be equal to on the left by P, right? And here we have B. P times P inverse, that's equal to I. On the right, multiply by P inverse. So here we have P inverse, right? So since this P is invertible matrix, right? So I can actually, this P also is inverse of something. That is the inverse of actually this P inverse. So if I just denote here, let's say this one, actually this Q as P inverse, then Q inverse will be P inverse and inverse, which is equal to by P, right? The property of the inverses of a matrix. Now from here, what we have here then? Here we will have, what is P? Q inverse, and here we have matrix B, and P inverse is just Q, that's equal to A, which shows that matrix B is similar to matrix A. So if A is similar to B, then B is also similar to A. In similar way, also you can actually prove C. Just here we need to follow two steps. And here it says that if A is similar to B, B is similar to C, then we should show that A is similar to C. I will leave this as an exercise to you Okay, very similar step. Just you need to take two steps like this. Then you will get, uh, okay, for example, here in C, just starting this one, A is similar to B means here we have P inverse times A times P, that's equal to B. And B is similar to C means we have some actually invertible matrix Q where Q inverse times B times, what is it? Here we have Q, that's equal to C. So from here, instead of this B, I can substitute that thing because they are equal. So here we have Q inverse. And what is B? B is P inverse times A times P. And here we have Q, which is equal to, on the right hand side, we have C. So here, what is this? Using the property of this inverse of a matrix, here we can just write it as PQ inverse times A times PQ, that's equal to C. Now, if you just choose this PQ as W, because the product of these n by n matrices, also it is n by n matrix. So that is W inverse times A times W is equal to C. That means that A is similar to C. All right. So any relation satisfying these three properties of theorems 4.21, any relation is called an equivalence relation. Okay, they are just, how to say, um, because that's the definition, all of the things are true. All right. So now we will see another important theorem about similar matrices. Let A and B be n by n matrices with A is similar to B. So when we just say that A is similar to B, immediately you should just think of this one, right? That means that here we have some invertible matrix P where A times P is equal to P times B. It's given here. And also we know that P is invertible, that is P inverse times P, that's equal to I. But about A and B, we have no idea. Are they invertible or not? We are not sure. So the first part says that the first one, determinant of A is equal to determinant of B. Okay. So how do you know that? Actually, proof, if we just start from here, for example, determinant of A, right, equals determinant of B. Now from here, since A times P equals P times B, from here we can just calculate that determinant of AB is equal to determinant of PB. And using the property of determinant, we know we have the theorem that determinant of A times B equals determinant of A times determinant of B. And which is equal to, on the right hand side, we have determinant of P equals determinant of B. So we know that's actually, why did I write B? It should be P, right? This one is P. A times P equals P times B. Also here we have determinant of P. So we know that determinant of P is not equal to 0. Why? Because it is invertible. So that means that since determinant of P is not equal to 0, we can just cancel out these two things, dividing both sides by determinant of P. Then here, what we have here, then determinant of A is equal to determinant of B. Okay, that is a proof of the first part. And how about the second part? I can continue here. We have more space here. Okay. It says that A is invertible if and only if B is invertible. Right? And also we can see that from here, since determinant of A is equal to determinant of B, right? If determinant of A is not equal to 0, that means that A is invertible. That means that determinant of B is not equal to 0, which implies that B is also invertible. If determinant of A is equal to 0, that means that it's not invertible. That means determinant of B is equal to 0, which implies that also B is not invertible. Okay. And also C says that if A and B are similar, I mean A is similar to B or B is similar to A, then A and B have the same rank. That means that rank of A is equal to rank of B. Okay. So now actually also we'll get this from here. Here we have rank of AP. Actually, that's equal to rank of A if A is invertible matrix. Why? Because null space of AP is the same as the null space of A. And also here, since PB is, here we have rank of PB is equal to rank of B. And also from here, null space of B is the same as the null space of PB. If from these two facts, combining these two facts, we will see that rank of AP is equal to rank of PB, which means that rank of A is equal to rank of B. And how about part D? A and B have the same characteristic polynomial. So that means a characteristic polynomial of A and characteristic polynomial of B, they are exactly the same polynomials. So to do this one, let's say characteristic polynomial of, let's say B, which is B minus lambda I. So we'll show that actually it is exactly the same as the determinant of A minus lambda I. We know that this one is, what is it? Determinant of B minus lambda I. That is characteristic polynomial of B, right? So actually maybe I can just write here P of lambda of A something. Anyway, so from here, determinant of what is B? Using the definition, we know that B is P inverse, right? From here, what is B? B equals P inverse times A times P. So if I just substitute this thing there, then here we have P inverse A times P minus lambda I, right? So now that thing again equals, I will just make a trick here or some kind of manipulation. P inverse AP, right? Minus here we have lambda. Instead of this I, since P is invertible, we can just write the thing. We can just write here P inverse times I times P, right? So what we have here, actually this number is just a scalar. I can either write it here or inside, it doesn't matter, right? So here P inverse, here we have P inverse, here we have P, here we have P. So I can just write it as something like this. Determinant of here, let me just write here P inverse, and here we have A minus, here we have lambda, and here we have I, and here we have P, right? If you just remove the brackets, we'll get the same thing. Here we have P inverse times A, and also multiply by P. Here we have P inverse times A times P. And P inverse times lambda times I times P, it gives us the second term here. And again, by using the property of determinants, we can just write it as determinants of P inverse, or actually, let me just write like this. Determinant of P inverse times determinant of A minus lambda I times determinant of P. And we know that determinant of P inverse times determinant of P, that's equal to 1. And that thing is equal to determinant of A minus lambda I, which is characteristic polynomial of matrix A. So since these polynomials are exactly the same, if you just put here equal 0, then we get the characteristic equation, right? That means that actually we get the same characteristic equations. That means the matrix A and matrix B, they have the same characteristic equations, which means that they have the solutions, and we know that the solutions of characteristic equations are just the eigenvalues. So if A and B are similar, then their eigenvalues are exactly the same. Okay. So now two matrices may have properties A to E, all these five properties in common, and yet still not be similar. Why? Because here we are saying that here we have one-way implication. We are saying that if A and B, right, if A is similar to B, then actually these are true. These five facts are true. But actually the converse is not true, because we are not saying that if and only if. If they are similar and they have these properties. If actually we have all of these properties, still we cannot say that A is similar to B. They may be similar, but they don't have to be similar. So to see this, let's just see this example. Consider matrix A, that is identity matrix 1, 0, 0, 1, and B 1, 1, 0, 1. So determinant of A, if you calculate this, that's equal to 1. Determinant of B, that's equal to 1. And both matrices are invertible, right? If you just check this, since determinants are not equal to 0, they are invertible. And rank of A, that's equal to 2. We have two, what is it, linearly independent vectors here. And also B, that's also equal to 2. And if we just calculate their characteristic polynomial, that is 1 minus lambda squared, determinant of A minus lambda I, determinant of B minus lambda I. We have the same polynomial. That means that they have the same eigenvectors, but still we can say that actually you will see that, but A is not similar to B. That means that you cannot find any matrix P, where here we have A times P that's equal to P times B, right? And actually here, what is A? A is just identity matrix here. This one is just I, just this example. So here we have I times P, which is the left-hand side is equal to P, right? If you multiply both sides by P inverse, here we have P inverse times A, that's equal to B. On the left-hand side, what we have here? Here we have I, and here we have B. Whatever you just substitute here, over we have this equation, which is not true, because identity matrix is not equal to matrix B here. Okay, another example. But how actually we are going to make use of that theorem? It means how here, if you just know that, because because here in this theorem, if we know that actually one of these properties fail to hold, then immediately I can draw the conclusion that these two matrices are not similar. That is how we actually make use of this theorem. Because if they're similar, then all of these five properties must be true. If one fails to be true, that means that A is not similar to B, or B is not similar to A. For example, in this example 2A, that A is this matrix 1, 2, 2, 1, and B 2, 1, 1, 2. They are not similar. Why? How do I know that? Here, if you just calculate the determinant of A is equal to 1 minus 4, that's minus 3. And determinant of B, 4 minus 1, that's equal to 3. For if they're similar, then their determinants must be equal to each other. Since these determinants are not equal, that means that they are not similar. How about in this example 2b, matrix A, 1, 3, 2, 2, and matrix B, the components are 1, 1, 3 minus 1. Also, they are not similar. Why? Because determinant of A minus lambda I. Characteristic polynomial of matrix A, if you just evaluate this, here we have lambda squared minus 3 lambda minus 4. And how about the characteristic polynomial of matrix B? Here we have B minus lambda I, that's equal to lambda squared minus 4. These two polynomials are not equal. They are not the same, right? For these two matrices to be similar to each other, actually, those five properties must be true. Actually, all of these properties must hold, right? But here, one of the properties fail to hold here. That means that immediately we can just say that then these two matrices are not similar. Okay. Now let's talk about diagonalization. That's our main task here, to diagonalize a matrix. So an n by n matrix A is diagonalizable if there is a diagonal matrix D such that A is similar to D. That is, if there is an invertible n by n matrix P such that P inverse times A times B equals D. So we are just saying that A is diagonalizable if it is similar to some diagonal matrix D. That is all about here. Let's just see one example. After that, we'll have a break and I'll continue after 10 minutes. So if A is this matrix whose components are 1, 3, 2, 2, is diagonalizable since if you just find this matrix and multiply by this, the result is, what is it? Diagonal matrix. Why? Here, if you evaluate this one, we'll just show that what is this A times P? A times P is 1, 3, 2, 2, and matrix P 1, 3, 1, minus 2, which is equal to 1 plus 3, that's equal to 4. If we have 3 minus 6, 3 times 1, 3, right? And 3 times minus 2, minus 6, 3 plus minus 6, that is minus 3. Here we have 2 plus 2, that's equal to 4. 2 times 3, 6. 2 times negative 2, it is negative 4. So here we have 2. And how about PD here? PD is P is 1, 3, 1 minus 2. D is 4, 0, 0 minus 1. So that's equal to, so here we have 4, 0. Here we have minus 3. 1 times 4, 0. Here we have 4, 0. Here we have 2. So these two things are equal. And what is special here? Actually, this A is similar to a diagonal matrix. That is actually what we're going to study here. Here, the important task is how do you find this P? That's also another problem here. Okay. So in the next video, we will work on this task, how we find matrix